So we move ahead with the next talk by Mr. Arnab Chakraborty of TCS Research. Welcome, Mr. Arnab.
First, I would like to thank Professor Kannan, Dr. Chandan Bose, um, uh, and Payal and the whole team for inviting me for this wonderful event. So I am Arnav from TCS Research. I am working here as a scientist. So basically, I am in a group of industrial manufacturing here. Basically, we deal with the projects related to the process industries, some process modeling. Uh, uh, those are relevant to the tablet coating, 3D printing, and many other things. So here we basically use some commercial softwares like ANSYS Fluent, MATLAB, or the COMSOL, and nowadays we are shifting our interest towards the open form because as you know that so for the commercial software the licensing is an issue, and another thing is that they are very costly. So and nowadays the open form has gained lots of popularity. So continuously we are shifting our research or our projects into the open towards the open source softwares. Yeah, so today I will be presenting the droplet dynamics in industrial manufacturing. This is the part of my work, so we cannot disclose all the results. So uh, so let's discuss few of them. Yeah, so the overview of the talk will be the background, the novelty and objective, the computational setup and validation of the model, modeling of spreading parameter and image processing based approach, the parametric studies, that is the effect of impact velocities, inclination angle and static contact angle, then the effect of non-sphericity of the droplet on its spreading dynamics, and then we will discuss some machine learning techniques in modeling the droplet dynamics, and I will conclude this talk. Now, coming to the background, as you can see that the droplets are present everywhere in the nature. So let's say one droplet is carrying some viral load or bacterial load, and it impinging upon some surfaces, the leaves or some surfaces, and it spreads. So based on its spreading, basically, so from the central, let's say this is the spreading or the maximum spreading. So based on the spreading, one can evaluate that how much the viral or the bacterial spreading will can damage the leaves or the surface. And similarly, in the second image, it is the disease transmission. And in the third image, as you can see, this is the surf zone where the waves are breaking off and produce some minute droplets or the sprays, and these droplets evaporates and change the local dryness fraction of that region. Eventually that contributes to the climate change. And the fourth image, you can see the disease transmission via sneezing of droplets. So it was a very serious issue during the COVID times. We all know that. Now, coming to the industrial applications, so all of those previously this mentioned applications were found in nature, but now coming to the industrial applications, that you can see that in so when a droplet is impinging on a wind turbine blade, eventually based on its dynamics and the trajectory, the erosion occurs. Okay. And how that erosion will propagate, that depends on the many things, the impact velocity of the droplet, impinging angle, the medium of the droplet, because when the droplet is impinging, it is not the fully water, it is somewhat acidic in nature, and sometimes that contains some aerosol particles also, because yeah. And let's say this is a gas turbine engine. When let's say these engines are going through the volcanic ash or some erosive medias, or let's say the yeah, so the droplet eventually come into it, and it erode the blades, the compressor blades. So droplet turbine blade interaction is another important aspect of the droplet dynamics. So there are lacunae in the literature we have listed here, that it is imperative to mention that most of these studies were experimental, and most of them reported the post-impact dynamics of the droplet and an inclination angle of 60 degrees. Above that angle, there is no literature available. So it could be observed from the few numerical studies also that the dynamics of the droplet changes in tangential direction above 70 degrees, while there is no mention about the post-impact dynamics on the droplet in the lateral dimension. So we need to carefully observe what is happening in the axial direction as well as in the transverse direction also. All the previous studies were focused mainly on the rebound and splashing regimes, but there is a substantial gap on the literature for the deposition regime, which is having direct implementation in the spray painting, tablet coating, 3D printing, and metal additive manufacturing. Because based on that, one can ensure the require efficiency or require efficacy of the coating. Okay, so all the previous studies talked about the dynamics of spherical droplet only. However, if the droplet is larger, or in case of polymeric droplet that encounters in many chemical applications, cannot sustain its sphericity and becomes non-spherical while impacting. So there is no literature available on the discussion of the dynamics of non-spherical droplet upon impacting an inclined surface. So the droplet turbine interaction is a major issue, as I mentioned above, and there are very few numerical machine learning based studies available for predicting the droplet dynamics. So we invoke a few of them, and very few numerical studies available for the dynamics of the droplet on plane having different kind of motions, whether it is a 1D translation motion, or it is a 2D or 3D translation motion, or a rotational motion, or combined of both motion. So we have investigated that. So that motivates us to further proceed with this study. So these are the motivation and objective of the present study, that all the previous studies were mostly experimental and reported at a higher Weber number. So in the present study, we numerically investigated these post-impact dynamics of the droplet on inclined surface over different Weber numbers, and the inclination angles and the static contact angle. Static contact angle means you are changing the surface every time. Now, the effect of droplet shape on the dynamics upon impacting an oblique surface over a wide variety of these influential non-dimensional numbers. And then the tangential and the lateral spreading factor, contact time, sliding length, the leading and trailing edge lengths, the regime plot of different dynamics, time evolution of the pressure, velocity contour, and the different dynamics over a wide variety of these non-dimensional numbers were investigated. And finally, we invoke some machine learning based techniques to predict its dynamics. So there are the challenges. So we know for the numerical modeling there are lots of challenges. So I'm not going into the detail of it. Now coming to the computational domain. So as you can see, this is our fluid droplet, and we have used water here, pure water, and this is the whole computational domain, and the surface is at an angle of alpha. So for the validation purpose, we have taken it for 80 degree, and the initially impact velocity u naught is 1.5 meter per second, and the size of the spherical droplet is 2 mm. Now, normally in ANSYS Fluent or in any CFD, commercial CFD software, people used to write UDF, their own UDF. But the thing is, sometimes this UDF doesn't work good. There are lots of patching issues. That's why we have developed our own image processing based techniques. That is, first we used to do the CFD simulations. We make its time resolve animations, and then from that we are extracting the image frames of the then we are converting these RGB images to the grayscale using in MATLAB, and then from the grayscale we are converting those grayscale images into the binary images using some proper intensity thresholding, and then we verify whether and then we are tracking these two extreme points of the droplet on the surface, and from that we are calculating the spreading diameter. And in a similar manner, we used to track the vertex of the droplet, how it moves downwards and upward, downwards during the spreading and upwards during the retraction. So then we compare these results with the literature and see if it is having a good match. If not, then we repeat to this step and change the intensity thresholding and again run this loop. So yeah. So and finally, after simulation and after obtaining all the CFD data, we have used the AdaBoost algorithm, and this table is as an input for this AdaBoost algorithm. So there are other algorithms also. So we have used only the AdaBoost here to show the machine learning based modeling, and this is the simulation setup. I'm not going into the detail. um, yeah, there are certain simulation assumptions also, that there is no heat transfer. We did not consider any heat transfer. Eventually that leads to the isothermal assumptions, and the droplet volume is constant. The liquid density is independent of temperature. The temperature has no influence on the viscosity of the liquid, and the liquid is incompressible, whereas the outer air medium is compressible. Now, coming to the results and discussions, before that, this is the grid convergence and the and the comparison of the schemes. So let's say this is a initial droplet and this is the inclined plane, and it hits the surface. Eventually it will go in the this downward direction. We are saying it the axial direction, and from the top view we can see the perpendicular surface on the same plane is the lateral dimension. So the we are calling the distance from the touching point to here is the trailing edge length, and from the leading edge to these touching points is the leading edge length. And yeah, so now coming to the grid convergence, as you can see, we have used the simple scheme of different mesh size, and finally we have chosen this 0.12 mm mesh as optimum, and 12 black elements were used. And further we varied the scheme, the simple and piezo. Now, simple is simple, that's over a piezo. That's why we use the simple in the overall simulations. Now coming to the quantitative validation and qualitative validation also. Now, so the first one is from the Guan et al. These are the numerical results. The second one is from the Sikalo et al. These are the experimental results. And third one is our results. And one can see they are good in agreement. So the qualitatively they are matching. Now coming to the quantitative validation. So we validate for the spreading parameter. So this xi is nothing but the instantaneous diameter of the droplet divided by the initial diameter of the droplet. So this is nothing but the non-dimensional spreading diameter of the droplet with respect to the time. And we compared our result with the experiments performed by Saho et al. And the error was found to be around 3%, which is below 5%, so it is acceptable. Yeah. Now these are the few videos of the effect of impact velocity on the inclination angle. So the first one is the Weber number, of 0.05. The second one is the 40. Third one is 80, and fifth one is 150. So from first one, you can see this always shows at a very low Weber number. It shows the deposition regime, and the second one is at Weber number 40. It is showing the rebound characteristics, and for higher Weber number, which is more than 40, kind of 80 and 150, they are showing the splash. So now we have varied the inclination angle to 45 degree and 60 degree. Now one can see that now at 80 degree the droplet is not breaking. That shows the prominent effect of the inclination angle. So these are the quantitative results. And we derive some correlations in terms of Weber number and the inclination angle. Okay, so these are the we have measured the different leading and trailing edge for different Weber number as well as for different angles. Yeah. So now these are the regime plots. These are the deposition and rebound and the splashing regimes. Now we varied the static contact angle. That means the solid material, the surface material, and that shows the different characteristics. Yeah, so these are the quantitative results again. Okay. So yeah, now coming to the machine learning part. So after obtaining those results, we have developed this AdaBoost algorithm, and we are calculating these matrices that shows the effectiveness of model. And that's say, and one can observe that it is the accuracy is 90% and the precision is 91% around. So we are still improving the accuracy and the precision can be improved. We are having we don't have a large data set. We are still running the simulations to acquire more data, then we can tune it finer. So these are the conclusions. So at a lower inclination angle and Weber number, a lower SCA or the static contact angle results in a greater spreading factor due to the hydrophilic nature of the surface. As the SCA increases beyond 90 degree, the surface becomes progressively more hydrophobic, and beyond 120 degree, it stands to be a super hydrophobic, leading to a decrease in a spreading factor. At a higher Weber number, the partial splashing was observed across all SCS up to the inclination angle of 30 degree. When the inclination angle reached 45, the droplet dynamics shift from splashing to rebound again due to the increased axial momentum transfer caused by the higher inclination angle. Now, the classification-based machine learning algorithm AdaBoost was developed to predict the droplet dynamics based on the CFD results. As I said, it shows the 90% accuracy, and still we are increasing its accuracy by providing larger amount of data set. So that is the conclusion. So here I am showing some ongoing projects, that is the droplet impacting on the translation surface, and here we have not introduced the turbulence. Soon we will introduce the turbulence to make exact what happens on the droplet impinging on wind turbine blades. And these are the we did this validation with these experiments by Zhang, and our results are giving around 3.5% error. And these are different regimes of yeah. So after impacting on the translating surface, yeah. So thank you.
Thank you so much, Mr. Arnab.